Hello everyone, my name is Will. I'm currently a postdoc at Google and I'm about to join Columbia Business School. But today I'm presenting some work I did during my PhD with my advisor, David Simchi-Levi from MIT. Okay, so I'm going to talk about online edge-weighted bipartite matching, but I'm going to present this as a general online resource allocation problem, which answers the question of how does a firm allocate limited resources to heterogeneous customers who arrive sequentially. So imagine you're a revenue manager at a hotel. You have fixed unreplenishable resources. These are like your stock of rooms for a given night. You're trying to sell these to different customers who want different types of rooms. So maybe this guy wants the 2-double room and she wants the king room, and they're willing to pay different prices. And any rooms that you offer and sell, your decisions are irrevocable. So the online problem is interesting because you don't know which customers are going to come in the future, and you're trying to figure out how to allocate these hotel rooms. So the objective is to maximize the cumulative revenue or the cumulative reward, and the trade-off is in this idea of immediate revenue versus future opportunity where I might want to withhold hotel rooms so that I can sell them at higher prices in the future. Okay, so let me formalize the mathematical model. There's n items. So each item, I'm going to think of it like a type of hotel room. So king rooms could be a type of item. King rooms could be an item. Queen rooms could be an item. And each item is going to have a discrete starting inventory. So if my hotel has 10 king rooms, then K is 10. And then each item has a known set of feasible prices at which it could be sold. So for example, my king rooms, maybe it has a rack rate, which is the default rate, of $300 per night, but it also has an advanced purchase rate of $200 per night. Now, so over the time horizon, my customers T arrive, and the dynamics are as follows. When a customer T arrives, I'm given for every item and every price, the probability, rho T, I of P, of the customer buying that item at that price if offered. Okay, and then my decision is to choose a single item which has not stocked out, so I still have that type of room available, and a single price to offer to the customer T. After that, I immediately see a purchase realization according to the probability given, and if the customer makes a purchase, I spend 1 unit of that item and I earn the price as revenue. And so this just corresponds to the picture from before where the hotel website is showing different customers, different hotel rooms. So our techniques also generalize to the case where you can offer each customer an assortment of multiple hotel rooms at multiple prices, which seems more realistic. But for this talk, I'm going to assume I'm offering a single hotel room, a single price. Okay, but I will consider a special case which I call the deterministic case. This is like the online matching setting where each of the purchase probabilities are either 0 or 1. And in this case, the problem reduces to essentially, when a customer comes, we observe the valuation or the maximum price at which they're willing to buy each item. And the decision is simply to choose up to one item to offer to the customer at their highest willingness to pay, which I'm assuming we know. And in this special case, the realization is deterministic. There's no purchase probability. I know that they're going to buy the item. So this is like the online matching, edge-weighted matching setting. Okay, so our goal is to maximize the competitive ratio. What does that mean? So there's some underlying arrival sequence A, which is characterized by the total number of customers and the purchase probabilities for each one. And I'm going to let alg of A denote the algorithm's expected revenue when the arrival sequence is A, and opt of A to be the best possible expected revenue I could have earned when the arrival sequence is A, and I knew it in advance. This is actually given by like an LP relaxation, where the inventory constraints only need to hold in expectation. But essentially the key thing is the optimum knows the arrival sequence in advance. And an algorithm is said to be C competitive if for every possible arrival sequence, I get this uniform guarantee where L divided by opt is at least C. Okay, so it's well known that with weights, when even one item has a very expansive range of prices, the best possible guarantee is C equals 0, and you can't do any better than that. So in this work, what we're going to do is we're going to allow the C term to depend on the weight sets. Okay, so we know that in the worst case, we can't do better than 0, but if we know the weight sets and maybe there aren't that many prices, can we do better? Okay, so our main result is the following. We derive a universal mapping F from price sets P to ratios that are in the range 0 to 1 minus 1 over E, such that, so basically for any subset of positive real numbers, F will give that subset a value. Okay, and then for an instance, we have a multi-price balance algorithm, which is minimum over I, F of PI competitive. So you take sort of the worst price set, the price set with the smallest value of F, that's the competitive ratio. And the first algorithm will attain this if the starting inventories go to infinity. And then in the deterministic case, we don't need the starting inventories to go to infinity. A different algorithm, multi-price ranking, will get you the same competitive ratio. And finally, these results are tight in that any randomized algorithm cannot be better than this when the price sets are chosen among what was given, even if we restrict to the large inventory setting or the deterministic case. Okay, so maybe this won't make more sense if I put this into the perspective of existing results. So a key thing to know is that if the cardinality of P is a singleton, then F of P is 1 minus 1 over E. Okay, so let's suppose all of the price sets are singletons. Each item has a single price. Let's look at the multi-price ranking algorithm. So it was previously shown, this was the first online matching paper by Vazirani in 1990, is that if all the price sets are just the same, so this is the unweighted setting, every item has a price of 1, then we can be 1 minus 1 over E competitive. This was extended to the setting where the price sets have size 1, but the different items could have different prices. This is the vertex-weighted online matching. So this was done in 2011 and a very nice analysis by DJK in 2013. In the multi-price balance case, so previously, a 1 minus 1 over E competitive ratio was known for the online B matching problem. So this is the unweighted setting. And if each item has a single price, we can show that this is actually equivalent to the AdWords problem. Even though the AdWords problem is phrased a bit differently where the bidders have budgets, essentially because the budget can only be converted to reward at a fixed rate, essentially it corresponds to each item having a single price. And finally, 1 minus 1 over E was known for the online assortment problem. This was the thing I was talking about where you can show a customer multiple items. So basically, our result captures all of these existing results when the price sets are singletons. But furthermore, for any price sets, we'll tell you the best possible competitive ratio through this F function. Of course, like I said earlier, if some price sets contains a very large number of prices with large ratios between them, then F of P will be 0, and our results will say the best possible competitive ratio is 0. Okay, so I'm going to now spend the rest of the time explaining the analysis and sketching the algorithm for multi-price balance. Okay, so what is the key new challenge here? The key new challenge is I have multiple prices, okay, so let's just consider a very simple example where I have one item and two prices. Okay, 150, 450. So what is the challenge here? Right? The challenge here is the first guy comes, he's only willing to buy at the lower price, and I need to decide, do I sell my items to him, or do I reject him and hope that later people willing to pay the 450 price will come? And basically, so I have these 5 hotel rooms. If I'm myopic, and I sell all of the hotel rooms at the lower price. If five, let's call them economy class customers, if they come, fill my hotel, and then I have no more space for 5 business class customers to come later, I'll get a ratio of the lower price to the higher price, which is 1/3. On the other hand, if I'm too conservative and I save all of my rooms for business class customers, but they never come, then my competitive ratio will actually be 0. So what's the best thing we can do in this case? It's a very simple exercise to show that if you set a booking limit where you're willing to sell at most 3 rooms at the lower price, then in both of these extremo scenarios, and in fact for any arrival sequence, you're going to always be able to get at least 3/5 of the optimum. And this is sort of the best you can do. Okay, so the idea is that we set booking limits, and the more rooms are sold, the higher the threshold becomes. Okay, and of course, we still have to deal with the challenge of multiple items, so it's not just an accept-reject decision. So here, if we only have 1 2-double room left, what we want is that if a customer comes and they're flexible, they're willing to take either one, we don't necessarily want to greedily put the customer in the 2-double room, which has a higher price, because maybe the next customer only is interested in the 2-double room, and then I have to reject them, earning a suboptimal revenue. So what's been done in the literature in this case is you have these penalty multipliers, where for every item, you have this Simchi-Levi, which is a number between 0 and 1, and you offer the item which maximizes the purchase probability times the price times the multiplier. So what you can do is, if the 2-double room is about to sell out, you can just give it a small value of psi I, which will disincentivize the algorithm from choosing it. Okay, so to combine these, what we're going to do is, instead of having a penalty multiplier, we have a virtual cost. Okay, so at each point in time, we're going to have lambda I be the virtual cost, and we offer to each customer the item and price which maximizes price minus virtual cost times the purchase probability. This is like the virtual profit, and we can reject the customer if this value is non-positive. So note that having a policy of this form simultaneously achieves the idea of reserving hotel rooms for higher prices, but also figuring out how to prioritize between different types of hotel rooms. And so our policy looks like this. And how do we set these lambdas I? So they're based on the fractions of initial inventory sold. So for each item, if Wi is the fraction of its initial stock which has been sold, then the virtual cost will be equal to a function phi I applied to Wi. So phi is an increasing function, and over time, the fraction sold increases, and the virtual cost also increases. What does phi look like for this king room? Let me just show you in this case. So remember, the 2 prices were 150 and 450. So phi is going to increase from 0 to the maximum price over the interval 0, 1 as the fraction sold increases from 0, 1. It'll look like this, and it's convex, and the key thing is the point alpha at which phi crosses the lower price of 150 is effectively the booking limit for the lower price. After the fraction sold crosses alpha, the algorithm will never offer the king room at the lower price again. The exact value of alpha in this setting takes this form, and it depends on the ratio from the high price to the low price. So let me explain where an expression like this would come from. So in general, how the analysis works is we do a primal dual analysis which separately solves for each item I, okay, the function phi I which maximizes the resulting competitive ratio guarantee. So the system of equations that you write down will depend on the price at pi. And then that's how you end up with expressions like this. And so each phi is going to map 0, 1 to the range 0 to the maximum price in the set. And so let me just show you a few more examples. This is what the function looks like when p is the price at 1 or 2 or 3. If it's just 1 or 3, which this is the curve you saw before, so it is slightly different. The curve will look different for any different price set. And we can also do this for continuous price sets. If the feasible prices are anything in the range 1 to 3, it'll be the smoother blue curve. So the blue curve doesn't have any kinks when the price range is continuous, whereas these green curves have these kinks corresponding to the booking limits. A few more remarks. The constant f of p is always greater than 1 minus e to the minus 1 over m if m is the number of prices in the price set. So for example, if m is 2, then the guarantee is at least 1 minus e to the negative 1 half. And note that this is sort of better than the trivial guarantee of 1 over m times 1 minus 1 over e. So if like each item has 2 prices, I can easily, using existing results, get a competitive ratio of 1 over 2 times 1 minus 1 over e by randomly choosing one of the 2 prices for each item and then using a vertex-weighted online matching algorithm to get this. But the optimal competitive ratio that we derive is strictly larger. So using these curves, you can get a better allocation than the naive allocation. The other thing I wanted to say is technically, the curve we have to use is not exactly the curve I just showed you. It's a rounded version of this curve where the kinks in the discrete prices have to be rounded to multiples of 1 over ki. And we do the rounding co-monotonically and show that this is the only way to get the rounding to work. Okay, so let me just conclude by summarizing all of our results. So I just showed you how the multi-price balance algorithm works. And I told you earlier that this achieves a competitive ratio of min I f of pi for large inventory instances. So I did say at the start we have this other algorithm, multi-price ranking, which gets the same competitive ratio for deterministic instances. So multi-price ranking will use the same phi functions, but instead of applying it to the fraction sold, you apply it to a uniform random seed between 0 and 1 that's chosen and fixed at the start. And finally, we show that you can't do better than f of p because we show that the adversaries optimizing an upper triangular graph of choosing the weights to minimize the competitive ratio, you end up with the same number as you get from the primal dual analysis. And I want to finish off by saying that in some sense this result to me is like a lucky coincidence. I don't have a good explanation of why the primal dual analysis gives you the same number as the adversary's optimization problem on an upper triangular graph. And I think this was also discussed in Devenir and Jane in 2012. And I think this is a very interesting thing that I would like to figure out in the future. And I think it's interesting future work. All right, thank you very much.
So, Ball and Perron also looked at a similar setting, that's like a single item though. So, and they had all these thresholds. Is there any like relationship between thresholds that you have in penalty function and those?
Yes, exactly. Yeah. So I actually didn't have this in the talk, but so there, for a single item, the thresholds look different than in our case. Actually, in the single item, the thresholds are lower. So you're less willing to sell at the lower price. With multiple items, then the thresholds are higher. That's a good question.
All right, let's thank you.